All right, so I want to talk a little bit about my theories on how the universe works, and I'm going to try to um, connect, you know, how the theory of everything should come together. All right, so I want to talk to you guys a little bit about my theory on time and space and how it all works. So I want to begin and just let you guys know that I've been trying to figure out for years and years how time and space works. And it started for me when I learned about the wave particle duality and how sometimes particles act as waves and sometimes they act as particles depending on whether or not they're how they're observed. So I came to realize that what was going on here is when when scientists, perform the experiment, the double slit, whatever, um, and the light passed through and it acted, and photons or electrons or whatever acted like waves. But when scientists tried to observe the the particles, they acted as particles. And how they did this was they set up an instrument to detect where what was going on, where the particles were, and this, that, and the other thing. They want to observe the particles, but because you can't you can't get the both the speed and the placement of a particle at the same time. So you can't know where a particle is and at the same time calculate its speed. You can only do one or the other. So the reason for this, when scientists use this device, basically what they're doing is they got to take a freeze frame in time of the photon or the electron, whatever they're using to perform this experiment. When they want to see where it is, they have to basically take a picture of it to see where it is using this instrument. They got to basically freeze time. So right there, a light bulb went off in my head, and I said, okay, so when they're observing it, it's acting like a particle when they're freezing time, and when they are just letting it run free, it's a wave. So I got to thinking, what if time is what's pushing these objects? What if time is the wave that pushes all matter in accordance with its mass through time space? Okay, so time is a wave that pushes all matter through time space in accordance with its mass. So the heavier an object is, the slower the time wave is going to push this object through time space, and the less massive an object is, the faster um, the time wave is going to push this object through time space. So then I got to thinking about Einstein's, what he said about time is relative. So if you think about this, I'm going to just draw a wave here. Okay. All right. This is a wave. Ooh, yeah, there you go. Okay. So let's say this is a person's wavelength. This is our wavelength. Let's say a man's floating in space away from all gravity, and this is his wavelength. This is how fast time is pushing him through time space. This is his wavelength, right? So over here, okay, you have, you're human. All right. Okay. Right. And this is, this wavelength right here, this spot right here is what you would say is the present for that person. Okay? So right here is basically your reality. What you're observing now at the very moment. Like right now, I'm looking at the computer screen. This is my present, my right now. So at this wavelength, excuse me, let me put that back. Of course. Always. Well, anyway. All right, so this is our present, okay? This is the space in which we exist. This is our wavelength, all right? Then also, you would have, you know, yourself here, the human here, the human here. These are all what you would say is the past versions of yourself. I mean, you already lived those, your wavelengths, you went through them, now you're here. This is your present. Okay? This is where you exist now, this is where you existed before. Okay? Now if you think about it, like what happens when let's say you flick a spring, okay? You see the spring as you flick it, you know, it looks like it's in multiple places at the same time. Also, like let's say you turn on a fan. When the fan is off, it's not moving, you know, it's in your reality as, you know, you can see the three blades. When you turn the fan on, the faster it moves, it looks like the fan blades, there's more of them, and it looks like it's just moving faster. You can't really understand why, because this thing is moving faster. It looks like there's more and more fan blades, you know. That's just my experience with that. But let's say the electron. This is an electron right here. Little tiny electron. Ooh, right there. Okay. All right. And this electron has its own wave. Okay. And because an electron is much smaller and has less mass, its wave is shorter and it's being pushed through time-space faster than we are by the time wave. Okay, I'll just finish that over that way. But also like us, you know, it has its present value, and then it has, okay, its past values, where it was in the past. All right. And I'm just going to go a little bit further in whatever. All right, so this is the present version of the electron right here. Right? This is his present. Whatever. This is the reality for the electron, this little space right here. But also, as you can see, in our reality, the past versions of this electron, okay, in our reality, you can see more of them. You got a past version here, past version here, past version here, here. Okay, so in our reality, on our wavelength, our time wavelength, because the electron's time wavelength is shorter and it's being pushed faster through time-space, there exists more of it in our reality. So this is basically the same electron, and we're seeing it in multiple places because this is our reality, and this is, you know, there is multiple copies because it's moving so fast. So this also explains entanglement. So like, let's say you change the rotation of this electron. It also affects this one, and this one, and this one, because you're changing the past, and which also affects future copies. Okay, so this is our reality on our wavelength, and as you can see, the electron is moving way faster than us through time space because it has way less mass, so it's existing in more places than just one place. We're seeing its past version, much like when you turn on a fan and the fan blades go really fast. You can't see each individual fan blade. You'd actually have to stop the fan in its motion to see the three fan blades. Okay, it's the same premises here. The electron is moving so fast, it's having duplicate copies of itself, and that's what causes it, you know, to act like a wave when you're not observing it. When you're observing it, you're just basically you observe it, and let's say you're observing it here, all right, and you got this, and you're like, okay, it's here in time space, and then you observe it here, and it's there in time space. But when you're not observing it in our reality space, it's in more places than just one. For this reason, okay. So the faster an object moves, it's in multiple places than once, according, you know, to time and space or whatever, to a larger object. All right, and it's the same thing. Well, let's say I'm going to explain this to you. Also, before I do that, this can also explain why our universe is missing mass. Because, okay, let's say the mass of this electron or whatever, let's say it's a quark or whatever, it has a mass of one. Let's just say. Now we can't when we measure the mass of an atom, it's missing a whole bunch of mass. Okay, because what you're doing is you're basically freezing or kicking out this quark to measure its atomic weight, or you're measuring just one single aspect of this. But just remember that quark lives in this present reality, in our reality, in multiple different places. So you can take the mass of its past selves and add them one, and then you got a mass of like 1, 2, 3, 4, 5, like 6. So you'd have a mass of 6, and here you are measuring the one quark, thinking it's got a mass of 1, but in reality, in our reality, okay, that quark exists in multiple places at once in our reality. So each copy of itself from the past is actually existing in our reality. So it's each one of those has a mass also, which is adding up. Okay, so I'd also like to go really quick and explain, like, all right, black hole. Oh, black hole. Okay, so we have a black hole here, and we have the event horizon. The event horizon is, for all intents and purposes, where time can't push an object. All right, let's go back a little bit first. Let's say we have a star. Okay. All right, we have a star here. Okay. Once that star becomes too massive for the time wave to push it, okay, because its wavelength is becoming so long and so stretched out. Once the time wave cannot no longer push that star through time space anymore because it becomes so massive, that's when a black hole happens. Okay, and basically time turns into like this, and at the event horizon, okay, at the event horizon, that's where time stops. So inside a black hole, I believe time reverses, much like you know how a wave happens. You got a wave that's going this way, and then it gets straightened out, and then all of a sudden it's going this way. It flips. The wave flips inside the black hole, and time starts moving backwards. The same thing with light. Once you go faster than light, you start going backwards in time because you have the wave of light like this, and then it's like it flips and starts going the other way, because that's just what happens. So let's say we have a star, and the star is here. Okay, this is a star, and it has a wavelength. Okay, and its wavelength is like this. Okay, blah blah, and that star exists here. It's on its wavelength here, 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 here. Now, because a black hole's time wavelength is straight, the reality of a black hole is going to be like this. This is the reality of the black hole, right? This whole line right here is its reality. So basically, you got the reality of the star here, right? And that it just goes on and on forever. Like if you observed a star from the event horizon of a black hole, you would see that star moving like a string. It would just be like a string. It would be you wouldn't be able to see it as a star. It would look like, like this, like a tube through space. Okay, so it would look like a tube, and you would be able to see every star, every planet, its past, present. It's past and present and future, or whatever you want to say, all at once, everywhere, because the time wavelength at the event horizon, there is no more time. Time stops. So other objects are still moving in space. You would be able to see them from the beginning of their lifetimes to the end of their lifetimes as like strings. And the same goes for smaller objects like electrons and stuff like that. When you get to some subatomic particles, in string theory, it's the same thing. You got a particle, and it's moving so fast that it looks like a string. Okay, to someone's reality. I mean, it could be the black hole reality. That's basically telling you that string theory is true. And it's like, if you ever watch Star Wars, when they go warp speed, how all the stars they stretch, and that's basically how it works. And this is basically the idea that I've come up with. So basically, everything works off your reality right here. Your reality according to time and your time wave. You have a longer time wavelength. Smaller objects are going to appear in multiple places at once, unless you're trying to observe it and you're freezing time, like taking a picture of it. Then you'll be able to see it wherever it is. But in nature, and when things are moving naturally, you got the electron moving so fast in our reality. Okay, because time is relative to the observer. In our reality, we're seeing this electron in multiple different places at once, because it's moving so fast. And this is basically my idea that I've come up with, and I just want to see if maybe somebody can elaborate on this, and see if maybe I got something going here, because I'm not really a physicist, but I've been studying this for a long time, and I just want to see if maybe my ideas might help and get something going here. So that's my idea and that's my theory. So if you guys think I'm crazy, just say it. But if maybe something I'm saying here actually works in the world of physics, just let me know.